Welcome to the stream. Hold on. It's on? I bet. There we go. All right. Welcome everyone to the stream. This is gonna be my final stream talking about linear algebra. My final stream. I will try everything as possible to finish everything I need to do. All right. We're not going to do every single linear algebra thing because, bro, there's like infinite things, but at least the goal is hold on, to finish a Khan Academy course, so we at least know like the basics,
It's Professor.
All right. But yeah. All right. Let's move on. Let me get the phone. I am streaming this an hour later than usual. The entire reason I'm an hour late is because, you know what? Let me just show you. Let me just show you what else I was doing the last hour. All right, what did I watch? Share this. All right, here's the browser. You already know. The entire goal for this stream is to finish these last 4, and then possibly even get to Unit 8, but we'll see. The entire reason I delayed by an hour is because I literally just spent the last hour watching this video.
Well, University of Oklahoma student is getting
ridiculous.
national attention.
I literally spent the last hour watching an actual like professor or a graduate grading that damn essay that went viral a few weeks ago. It's 50 minutes, so yeah, I basically spent the last hour watching this. Jesus Christ. I ignored this entire situation. I didn't even read the essay because I just didn't want to I didn't want to think about it. And then I watched this video. Oh my god. Oh my god, that was bro. I don't even know what to tell you, bro. That essay is genuinely the stupidest thing I've ever seen in my life, bro. Oh my god. Is it switched offline? Yes, because I'm on Wi-Fi. Like, I used to be on Ethernet, but like I moved, so I'm not on Ethernet anymore, and I want to make sure that, connection's stable and all that. And there's more viewers on YouTube, so it's what it is. It's not just bad, it's atrocious. Oh well. Good video, guys. I recommend y'all should watch this, and let's move on. So yesterday we just learned about inverse matrices, and they're basically ways to invert a transformation. So for just like how x squared times x to the negative squared is equal to 1, a matrix times an inverse matrix equals I, where I is a matrix that has 1 on the diagonal, like this. Yeah, what was it? These are linear algebra. My way of learning is just use Khan Academy here, and then I use Prof. Dave, his playlist on linear algebra, to learn the topics. And then the thing is, Professor Dave only summarizes, exactly what you need. So if you want further understanding, I got, 3B1 Brown's iconic linear algebra playlist. And once we get to calculus and differentials, y'all already know I got these two. Neural networks are not part of this, so ignore that. Good morning. Good morning, Achieve Unlocker 69999. There's also dot products, but that's like physics stuff. I don't know. What do you think about organic chemistry tutor? I'm not gonna lie to you, I don't use him that much. I don't use him because I rely on Professor Dave. I don't use him. I don't use it that much. I will say, when I did chemistry, I did use organic chemistry tutor because he's a chemistry guy. I will say I used his stuff for chemistry. Paul's online math notes. Alright, bet. Dot product is probably just one formula that I don't care about. Alright, let me try and get 100%. Consider this matrix, find the inverse. So alright, let me just write down everything, all the basic linear algebra stuff that I'll remember. So you have matrices, right? You have addition and subtraction, /sub, scalar, multiply. You have RREF, reduced row echelon form, to the Gaussian elimination shit. You got determinant. You got matrix multiplication, and you have inverse. Just write did 250 times. I don't want to write it on a freaking mouse, okay? Maybe on my notebook. Getting bent teeth from algebra? Hey, wait, that's actually a good title. I might use that. What do I write for my biology assignment? It's 250 words. 250 words is so short. That's on you, bro. Alright, so if you want to get an inverse of a 2x2, so I have two different strategies. If it's 2x2, just do the shortcut method, so which is just switch the 2, 7 and 2, switch the diagonal, the main diagonal, and then for the other diagonal, just switch the sign. And then divide each number by its determinant. So 7 times 2 is 14. Minus 16 minus 2. So divide everything by -2. Right? -4, -1, -1. Alright, bet. Enable it. I smoke you in Wordle. Okay, so what? I'm not a vocab guy. I'm a math guy, or at least a STEM. I mean, biology is also like something that's like okay-ish. I can learn that. At least not the doctor side of medicine or biology. Like I don't want to do that. That shit's scary. Anyways, -1, -10, -2, -1, and then the determinant is 10 minus 2, so 8. Yeah, 8. So -1/8 again. -1/4, -5/4. Wait, can I ask if anyone's in the chat studying biology? Isn't that shit literally just memorizing everything? Wait, why am I have a big field. I feel like I can just like make everything super small. -3, -6, -2. Divide everything by the determinant, which is 15 minus 12, so 3. So -5/3, -2, 3, right? -3, -1. There's a lot of writing. Linear algebra is mostly memorizing too. Hey, you got a point. You got a point. linear chem is memorizing plus math, which I can agree with, especially if you're like, you know, if you're doing the conversions and shit. But like math is just a little bit, not that much. Bio's memorizing. That is, like, in my experience, biology is literally just memorizing everything. That's literally how my teacher taught it. And the thing is, she was like, yeah, I'm sorry guys, it's just that there's so much to know and we don't have a lot of time, so y'all just memorize everything, which is unfortunate, but whatever. -1. 7 minus 9, so -2. So -1/2. 9/2. 1/2. -7/2. Alright, alright. Oh, scared me there. I feel like memorizing a process is different from memorizing math. Yeah, I feel like, you know, if it's a math, there's definitely a lot of stuff to memorize. But like memorizing math is different from like memorizing biology, bro. Because like math is just rooted in very basic fundamentals. But like biology, remember that biology is like, you know, so many levels ahead. Like you cannot find like basic fundamentals to biology without just memorizing shit. Like for example, photosynthesis. You know, how does a plant convert the sun's light or heat to food? Yeah, like where do you go? What's the fundamentals? You have to go down to the atom. Like you have to remember how each individual atom and, you know, each molecule in the plant interacts. No. Hey, I don't know what to tell you, bro. Mages are not even hard, just annoying. I can agree with that. I can agree with that. Also, holy shit, what happened here? A system of 3 linear equations is represented by blah, 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 blah. So you have this and x and b. This is the inverse of matrix A. Solve the system. Oh shit, what? Oh, so you have the inverse, and you have the linear, and you have the original matrix, and you have the inverse. Oh, I understand it. This is why we learn inverses. So you have A, I think you guys can see, AX, X is a vector, right? Yeah, this is a vector because it's one column. AX, okay fine, let's put that arrow, equals B, arrow. And we have to find X. So we have to multiply both sides like this. And you have to put it on the left side because multiplication is not commutative. Fuck, man! So I have to do multiplication twice. Kramer's rule. Do I have to know that to solve this? This is why you watch the videos. Okay, fine.
We saw that we could take a system of 2 equations with 2 unknowns and represent it as a matrix equation, where the matrix A are the coefficients here on the left-hand side.
Twice,
the column vector X has our 2 unknown variables, S and
really
T,
long.
and then the column vector B is essentially representing the right-hand side over here. And what was interesting about it, then that would be the equation A.
God damn, I skipped the previous video also.
Matrix A.
Oh wait, no wait. No, don't worry. This is where I am also.
Times the column vector X being equal to the column vector B. And what was interesting about that is we saw, well look, if A is invertible, we can multiply both the left and the right hand sides of the equation. And
so I do need to learn Kramer's rule. Or whoever Kramer. I keep thinking of Craner.
On the left-hand sides of their respective sides
Goon
by
Cam
A
or me
inverse, because remember, matrix
Cam for what?
multiplication order matters.
make
We're
a
multiplying
video
the
like
left-hand side of both sides of the equation. If we do that, then we can get to essentially solving for the unknown column vector. If we know what column vector X is, then we know.
When have you ever wanted to do anything in math? Bro's a new gen. I have done study streams in math for like even like a year and a half ago. I was doing this shit. Almost 2 years ago, I was doing this shit.
Know what S
Y'all
and
don't know
T
ball.
are, and then we've essentially solved the system of equations. So now let's actually do that. Let's actually figure out what A inverse is and multiply that times the column vector B to figure out what the column vector X is and what S and T are.
Oh wait, yeah. Oh wait, my bad. I forgot that this one equals I, so I can just cancel these out. I forgot. These are matrices, so I just like, you know, it's not algebra. It's not like regular algebra. So I just don't know when to cancel shit out anymore. So okay, I just have to multiply these two. Okay, that makes life a lot easier.
So A inverse.
We learned this up in year 2, by the way. You're not smart. Okay, then teach it to me. Oh wait, maybe you're talking to someone else. My bad.
Is equal to 1 over the determinant of A. The determinant of A,
Imagine I get to study stream 67. How many days do I have left? If it's study stream 12, now we're not gonna get to 67 before school starts. So I have to do a study stream in college, like in my dorm. Hey, I wouldn't mind doing that, honestly. I don't know if the internet's good there, but we'll see.
A 2 by 2 here is going to be 2 times 4.
They gave you the inverse. Oh yeah. If anything's an inverse to anything, to any system, it always goes to identity. Alright, bet. So, and the thing is, Khan Academy gave me the inverse. So it's a lot easier. I just multiply the vector and A. So but usually you don't get the inverse, so you have to solve for the inverse and then multiply it to B. So that's a lot of steps, bro. And you have to make sure you're not wrong any of them. Oh my god.
Minus -2 times -5. So it's going to be 8 minus positive 10. 8 minus
Wait,
positive 10.
what am I doing here? What?
Minus 2, 1 over, determine A inverse of A, 8. So this would be...
Oh, okay. He's doing the thing I already know. I wouldn't write time multiplied. I don't know why. It just makes it a little more complicated for me. Because like you have to remember the 1 over. I would just say divided by. But I think the reason is because you can't divide a matrix by something. But like it's the same thing anyway. I don't give a shit. I hate roommates. I do have my own. I don't technically have roommates. But I do live nearby some people. But we'll see. Honestly, I'll definitely stream when I'm in college.
Negative 1/2.
Something more
negative chill. 1/2 times 5 is negative 2.5. Negative 2.5. And negative 1. Back
right,
at negative 2.
Please don't use decimals. Please, Salkan. You've done this like 3 times already. I get scared every time. And then just multiply. So just 7 times the first column, negative 6 times the second column. Wait, what? Oh, that's 6. Phew! Yeah.
We have just shown that this...
It's a little pedantic to say multiply by reciprocals of divide. What? Alright, bet. I hope we get an E+. Hey, at least you did say F. Yeah.
Is -1. Or we could even say that T is a negative way of saying that. Said this in the last video.
Okay, so this is the final form. Wait, what is Kramer's rule? This video does not say that. All right, let me go. Should I even learn? Not, you know, let me go on a tangent a little bit.
Hey everyone, I've got another quick footnote for you between chapters today. When I've talked about linear transformations so far, I've only really talked about transformations from 2D vectors to other 2D vectors, represented with 2x2 matrices, or from 3D vectors to other 3D vectors,
losing my patience.
represented with 3x3
What is
matrices.
134 divided by 2? I don't know. 66? No, 6. Oh my god, bro.
But several commenters have asked
figured it
about
out.
non-square matrices, so I thought I'd take a moment to just show what those mean geometrically. By now in the series, you actually have most of the background you need to start pondering a question like this on your own, but I'll start talking through it just to give a little mental momentum.
So I'm gonna guess if it's not square, it's only gonna move 2 vectors.
It's perfectly reasonable to talk about transformations between dimensions, such as one that takes 2D vectors to 3D vectors. Again, what makes one of these linear is that grid lines remain parallel and evenly spaced, and that the origin maps to the origin. What I have pictured here is the input space on the left, which is just 2D space, and the output of the transformation shown on the right. The reason I'm not showing the inputs move over to the outputs like I usually do is not just animation laziness. It's worth emphasizing that 2D vector inputs are very different animals from these 3D vector outputs, living in a completely separate, unconnected space. Encoding one of these transformations with a matrix is really just the same thing as what we've done before. You look at where each basis vector lands and write the coordinates of the landing spots as the columns of a matrix. For example, what you're looking at here is an output of a transformation that takes I hat to the coordinates 2, -1, -2, and j hat to the coordinates 0, 1, 1. Notice, this means the
3B,
matrix
1B.
encoding our transformation has 3 rows and 2 columns.
So Z stays
which,
the
to
same.
use standard terminology, makes it a 3x2 matrix. In the language of last video, the column space of this matrix, the place where all the vectors land, is a 2D plane slicing through the origin of 3D space. But the matrix is still full rank, since the number of dimensions in this column space is the same as the number of dimensions of the input space. So if you see a 3x2 matrix out in the wild, you can know that it has the geometric interpretation of mapping 2 dimensions to 3 dimensions, since the 2 columns indicate that the input space has 2 basis vectors, and the 3 rows indicate that the landing spots for each of those basis vectors is described with 3 separate coordinates. Likewise, if you see a 2x3 matrix with 2 rows and 3 columns, what do you think that means? Well, the 3 columns indicate that you're starting in a space that has 3 basis vectors, so we're starting in 3 dimensions. And the 2 rows indicate that the landing spot for each of those 3 basis vectors is described with only 2 coordinates, so they must be landing in 2 dimensions. So it's a transformation from 3D space onto the 2D plane. A transformation that should feel very uncomfortable if you imagine going through it. You could also have a transformation from 2 dimensions to 1 dimension. One-dimensional space is really just the number line, so a transformation like this takes in 2D vectors and spits out numbers. Thinking about grid lines remaining parallel and evenly spaced is a little bit messy due to all of the squishification happening here.
Listen to the
So
people.
in this case, the visual understanding for what linearity means is that if you have a line of evenly spaced dots, it would remain evenly spaced once they're mapped onto the number line.
Alright, cool.
One of these transformations is encoded with a 1x2 matrix, each of whose 2 columns has just a single entry. The 2 columns represent where the basis vectors land, and each one of those columns requires just one number, the number that that basis vector landed on. This is actually a surprisingly meaningful type of transformation, with close ties to the dot product, and I'll be talking about that next video.
Product.
Until then, I encourage you to play around with this idea on your own, contemplating the meanings of things like matrix multiplication and linear systems.
Alright, what is Kramer's rule? I want to know what I don't want to be
Professor
gatekept
Dave.
anymore.
Let's learn Kramer's rule.
He knows a lot about all kinds of stuff. Professor Dave explains.
Next video is gonna be ranking the greatest gooners. If my editor actually sends me the fucking video, bro, come on, so annoying, bro.
By now, we are quite familiar with systems of linear equations,
Damn,
as
bro,
well
that
as a
short
couple
hair.
of ways to go about solving them.
Damn, bro,
But
got a
now that we
haircut.
have also learned how to find the determinant of a square matrix, we are ready to learn a totally new way to solve these systems. So let's do that now. Say we have the following generalized system of equations to solve. We know that we can do Gauss-Jordan elimination.
Yeah.
But if we don't feel like doing that, there is another way, and that's something called Cramer's rule.
Yeah.
This rule involves setting up the coefficient matrix that corresponds to the system and replacing certain columns with the constant terms that are shown on the right side of each equation. The
does that
rule
mean?
states that the ith component of the solution, meaning a particular one of these variables, can be found by taking the determinant of the matrix with the ith column replaced by the constant terms.
Hey, what?
And
Oh
then
my god, what is this? Oh my god. Wait. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so okay. So x sub of I, so which one, is equal to the determinant of a. What? A to the I? What is A1? If that's a capital A, there's only one A.
dividing
mean?
that by the
Ith component of the solution. What? What?
determinant of the coefficient matrix, found by taking the determinant
This is
of
not good notation. I'm not gonna lie, bro. What?
the matrix with the ith column replaced by the constant terms, and then dividing that by the determinant
I
of the
need an
coefficient
example.
matrix. So if we wanted to solve for the first variable, x1, we would replace the first column with these constants to get matrix A1. If we wanted to solve for the second variable, x2, we would replace the second column with these constants to get matrix A2, and so forth. Let's take this pair of
give me-
equations
I need an
and
example,
run
bro.
through
This
a
is
simple
ridiculous. This is
example.
weird.
Setting up the coefficient matrix, we get 1 and 3 on the top row, and then 2 and 2 on the bottom row.
Okay.
Let's go ahead and find the determinant of this matrix, as the determinant of the coefficient
Okay, so x sub I. Okay, the determinant is -4.
matrix will be used no matter which variable we solve for. If you need to remember how to do that, check out my
Don't worry,
previous
Professor
tutorial
Dave.
on this
We
subject.
got this.
Otherwise, let's just multiply the 1 in the top left by the 2 in the bottom right, and then subtract from that the product of the 3 in the top right and the 2 in the bottom left. This gives us 2 minus 6, or -4.
Right?
Now let's talk about the matrix that goes on top. For the first variable, x1, we will have to replace the first column of the coefficient matrix with the constants.
So the determinant of this.
5 and 6 that we see on the right side of these equations. And then we will find the determinant of this new matrix. This will be 5 times 2 minus the quantity 6 times 3, or 10 minus 18, which is -8. Then to solve
Bro,
for
I'm gonna
x1
get so confused. This an absolute value because like I was thinking of making it positive. I think I just have to remember that matrices are capital letters.
we simply divide the determinant of the altered matrix by the determinant of the
So to
coefficient.
find, what is x1? Is x1 just all the x's on the first column? Okay, that's okay. Yeah. Oh, because you're using x1, not like xyz. All right. So okay, let's say this x and y. So let's solve for x. Replace x in that column with the answers. Find the determinant. That determinant divided by the original determinant. You have x1 is 2.
thing.
And then you do the same thing for next
The only
one.
difference is that we will replace the second column of the coefficient matrix with 5 and 6.
Is it really faster though? I guess this is another way to solve it. I feel like I would, if it's just something simple like this, I feel like I would just use the traditional algebra method.
Rather than the first, because we are solving for the second variable.
Okay, and then get this determinant and that determinant divided by the original determinant, and x is 1. Alright, bet.
It's like a lot of work, when we could have solved this very quickly
okay.
by
Taking the words right out of my head.
substitution or elimination. But the thing to remember is that systems of equations can get very complicated, and solving 10 equations with 10 variables won't seem so easy by previous methods. Kramer's rule is a simple algorithm that works precisely the same way for any number of equations with that
Mod B. No. His major's gooning. Haha, funny. Guys, I've said this in the previous streams. Bro, y'all gotta think of some better jokes than just gooning, bro. I get it. The next video I'm making is about gooning. Why? Because it's like a really popular thing. But like, if you want me to like be honest, bro, it's just lame as fuck. Like, I get it. Alright, chill.
same number of variables, so long as the system has a
How about pooling? That's a new word. That's an interesting word. Maybe. We can get some other stuff. Code Labs either for linear algebra. Hot tub.
a unique solution. If the coefficient matrix has a determinant of 0, we will not be able to use this rule, as there is not one unique solution. But this is easy to spot, as we would need to divide by 0 when solving for any variable, and of course that's not possible. Now that we are warmed up, let's look at another example, this time with 3 equations and 3 unknowns. First, let's set up the coefficient matrix and find its determinant. If you need to practice finding the determinant of a 3 by 3 matrix,
I know how to do it. It's just like, it's just long, bro. I feel like linear algebra is a subject that I'm not gonna like when I actually like study it in school, because like, God, it's so long.
Tutorial now. Otherwise, here we will just skip ahead to knowing that the answer is 12. Now let's set up the 3 other matrices that
Okay, so just replace the first, second, third column with the answers.
will be involved
and
in
then get their determinants, and then divide A1 with A, 2, second one is 1, next one is -4. So those are the answers. No shit, but this is why we make algorithms do it. But it doesn't hurt to learn it yourself. It does not hurt to learn it yourself. You learn it yourself and then you learn the algorithm. You let computers do it, but only after you learn it yourself. But you know what? Let's try it by ourselves. Equals plus z equals 3 x minus y minus z equals 0 x plus 2y plus z equals 0. Majoring in math? I'm actually majoring in physics. Math or physics is fine with me. I'm fine majoring in physics because physics is applied, you know? if you major in math, bro, it's like you have two career paths: PhD and teacher. That shit lame as hell, bro. I ain't even gonna lie to you. Okay. Let's do this. 2, 1, 1, 1, -1, 2, 1, -1, 1. I'm reading the teacher one. Nice. Good job. Make a video about the hot tub epidemic. What? If you're talking about like hot tub live streams, bro, you have to be like 100 years like out of the internet, bro. All right, let's find the determinant. So it's 2 times the determinant of this one minus the determinant of 1 minus 1 1 1 plus the determinant of 1 minus 1 1 2. Letting Heavy to get a spot on Denmark's Math Olympiad team. Awesome. Right after my algebra classes. Yes. Fought you. Alright, what's the determinant here? -1 minus, so that's 2, right? This is -1 plus 2, so 6 minus 1 plus 1, 2. 2 minus 1, 3. So 4, 7. The determinant is 7. All right. So let's say like I don't know. What's a funny one? Let's use phi. Why not? Let me use a random letter. Det of phi equals 7. And this is where it's gonna get painful. Let's get x and replace this one with 3, 0, 0. You have to do this 3 more times. Alright. So let's say that the det of phi, but let me replace it with x. Phi sub x equals, okay, 3 times, what is the determinant of this one? I feel like I can just do this mentally. 3 times 1 -1 plus 2. 1 minus 0 minus 0, so nothing, plus 1 times the determinant of this, which is 1, 0, plus 1, 0, 0, so 0 minus 0, 0. Okay, so the determinant is 3. Now let's do phi of y. Did you know F777 made music for Run 3? I did not know that actually. Interesting. Alright, let's do 2 times the determinant of this, which is 0. Wait, what? Oh shit, I messed something up. I messed something up, didn't I? Oh no, I didn't. It's 1 times the determinant of that, which is 0. Alright, good. I didn't mess it up. I thought I did. So this one, 2 times the determinant of this, which is 0. Alright, good. Minus 3, the determinant of this, which is 1 plus 1. 2. Right, 1 minus minus 1. 2 plus 0. The answer is negative 6. Alright. Determinant of phi of z. That's an ugly one. Hell no. Oh, hell no. Alright. I'm so lost. Hey, I apologize if, you know, y'all did not watch the previous streams. I can't do much to really help you here because math is a subject that you really have to start from the beginning and work your way up. Why'd I put Y? I'm Foursquare. I'm the youngest person ever twice. Alright. It's going to be 2 times 0. So any time you have an entire column, the bottom two columns have bottom two rows have a 0, then you immediately know the determinant of this is 0. 0 minus 0, 0. Minus 1, 0. Oh shit. I zoomed in. So 1 times the determinant of 0. Yeah. Plus 3 times 2 plus 1, 3. So 2 minus minus 1, 3. So the answer is 9. Okay, so x equals 3 over 7. Y equals negative. Fuck! No, I'm not reading that number. And z equals 9 over 7. That's the answer. Right? How old is fan base? They're like 4 years old. Are you fucking kidding me? Of course I get it wrong. Oh my god, I got these ones right. How did I get the original determinant wrong? See, bro, like, it's not even hard. It's just, there's so many steps that I get one of them wrong. I'm gonna fucking die. Fuck. Fuck, bruh. Let me try this again. 2 times minus 1 plus 2, 3 minus 1 times 1 plus 1, 2 plus 1 times 2 plus 1, 3. So 6 minus 3 minus 2 plus 3. 4 plus 3. Wait, what? I'm getting 7. Oh, hell no. What did I get wrong? How did he get 3? Yeah, it's minus. What did I do wrong? Yo, what did I do wrong, bro? I got these three right. What did I get wrong? 2, 1, 1, 1 minus 1, 2, 1 minus 1, 1. The determinant is 2 times the determinant of this, which is just minus 1 minus 2 plus 2. Oh no, oh no, oh no, oh no, oh no. That's embarrassing. It's just minus 1 minus 1 plus 2. Oh, that's bad. Yeah. Minus 1 plus 1, 2. Right, 1 plus 1, 2. Plus 2 plus 1, 3. So 1 minus 2, negative 1. Oh, no, it's 2. 2 minus 2 plus 3 is equal to 3. So this is 3. It's all because I messed up this determinant. Oh my god, bro. See, it's always like one thing, bro. We can't hear you. Stop trolling, bro. It ain't working. Anyway, so now that we have this, x equals 1, y equals negative 2, z equals 3. Fuck. You are mute. Yeah, sure, buddy. I need to call my editor, bro. He's not answering. He's so fucking... Okay. Is your entire fan base just incels? I don't think they're incels. They're just children. Hey, I mean, can you really blame me? Can you really blame them? I mean, it's the content that I'm making that's like super stupid. So obviously, if I stream, there's gonna be quite a few dummies. Whatever. Alright, let's see if we can solve this equation. Alright, let's just do this. Let me finish this real quick. Solve the system. So they already gave the inverse. All I have to do is just these cancel out, and then x is just here. All I have to do is just multiply b with this inverse. So let me just do that real quick. Do this s times 3, 5, negative 1. 1. Alright, so the answer is 3, 9, negative 6, 0. 5 is negative 25, 25, 20, negative 1, 0, negative 2, negative 5. Answer. So Oh wait, hold on. Wait, what? Oh no, I think I'm dumb. I'm only 16 factorial. Wait, this is XYZ. Wait, now I'm confused. How do I solve this? I actually like forgot. Like I don't remember. Well, imagine the equations in the matrix and the vector is what we were substituting. Wait, wait, oh my god! I'm actually like lost, bro. Okay. Because like I multiplied it. Obviously you put inverse on the left side to cancel them out. You put A on the left side like this. And then you multiply it like this. I have this 3x3 matrix. I need one answer. It's row times column. Yeah, I just like, you know what? Let me skip this one. I actually want to know how they solve this. I feel like I'm there's like one thing I'm missing. A negative 1 is a 3x3 matrix though. Let me think about it. Probably super simple. I just don't remember. Ah, that's why you have to add them together. See, that's like one step I'm missing. Because you can think of 3, 5, and 1 as just X, Y, Z. Like that. And then once. Yeah. 3 times the first one plus. Yeah, I forgot. The next one. Minus this next one. Ugh. Annoying. Girl, this is easy math. 3 out of 10 rage bait, not bad. Millen's given the following equation: x times a times x minus b equals 0. Wait, what is 0? Does it mean like every single value is 0? Where a is an invertible square matrix. X is an n-dimension vector of variables. Ugh, it's so hard to like think about this stuff. I feel like wire my brain differently. B is an n-dimensional vector. Okay, of constant numbers. And 0 is an n-dimensional 0 vector. Okay, so it is nothing. Here's how she solved for x. A1 times x cancels out. What is what is this guy's mistake? I think it's this one, right? It's not like it's necessarily equal to 0. What is the answer? I actually genuinely don't know the answer. Like, how are you supposed to know this? Bro, like, it looks fine. Like, the arrangement is the same. A1 and A cancel out. You have x minus b equals 0. But maybe, I think this one's the issue. I think it's this one. No? We solve other matrix equation in ways that are very similar to how solve. Okay. Matrix multiplication is not commutative, so it matters. Okay. We cannot undo matrix multiplication with division. In our case, it seems like Milan multiplied both sides of the equation by... However, in order to multiply the left side by A1, she was supposed to multiply both terms. Oh. Whirow, it's easy. Oh, because she have to, because she multiplied only, she only multiplied. She had to multiply all of it by A1. It's hard to visualize, I'm not even gonna lie to you. Because remember, A times X is one term, B is another term, so she has to multiply it to B also. Yeah. Okay, I just couldn't visualize, I just couldn't find it. Let me restart. A system of linear equations is represented by the following matrix equation. Solve the system. Okay. Oh, this is gonna be so boring. So I have to get the inverse. So oh wait, I have to do the other way, sorry. Inverse 9,4. I have to do the inverse, which is -3. Then divide everything by the determinant. The determinant is -14 minus +12. So -2. -2. So divide both sides by -2. So 1 3/2 -2 -7/2. The formal proofs are more interesting in linear algebra. What are you doing? Eigenvalues? I probably won't do them, honestly. It's way too advanced. I didn't even do calculus yet. I wanna get to calculus. We'll continue linear algebra when the time comes, but so this is about the limit, honestly. All right, now multiply it. So you have 9. What is that? 9 and negative 18 plus 4. 3, 6, 9, 12. 6 and 7, 14, 21, 28. Negative 14. So x is 15, y is 32. Negative. Am I right? Nice. Linear algebra 2. Damn. Solve this. Okay, thank God, bro. Your Khan Academy just gave a 3x3. It's basically gonna make it 4 times longer. Because getting a determinant... Oh, not 4, 3 times longer, bro. God damn. Equals, I have to put it on the left side. So 11, 3, 1, 1, 0, negative 8, 7, 2, 3. Negative 4, negative 2. So you have negative 44, negative 12, negative 4, plus, just put that there, negative 2, 0, 16, plus 21, 6, 9. So 40, negative 46 plus 21. So that is negative plus 21, negative 25. Negative 6. 4 plus 16, so that's 12 plus 9, which is 21. Alright. Learn car mechanics. I wish. I don't know how to learn that, like, any of that, though. Now let's given the following equation. Okay, that's how she solved for x. Oh, you can't divide by matrix. Following matrix system. Solve the system. Okay. Get the invert. Okay, so a negative 1 equals, what's that? 4, 4, 2, 1, 3 times 1 over the determinant, which is 8 plus 3. 8 plus 3, so 11. So it's going to be 4 over 11, 3 over 11, 1 over 11, 2 over 11. right? 8 minus minus 3. Lecture 4 in uni. Okay. Cool. I have to multiply this number by -2, 11. So that's so -8 over 11. -2 over 11. Plus 33 over 11. 22 over 11. Actually, I should really do it improper. What is 33 minus 8? 25 over 11. Okay, that's the answer. When you're in higher maths, you don't do mixed number, you just do improper fraction. Is my answer? What? Bro, how's it wrong? How'd I get it wrong? Four and 2 are switched. 3 and 1 are positive. Get the determinant of the original. 8 minus minus 3. Right, you multiply these two. Fuck! Fuck. Every time, subtraction always confuses me. Because it's minus, but -3 times -1 is positive. So it's going to be 8 plus... No, fuck. 8 minus 3. 8, because it's 3, minus 3. 5. Fuck! Bro. It's always that one little thing with the fucking negatives, bro. Stupid ass. Fucking bitch, man. Oh my god. That's annoying. Okay, we just did this. Oh wait, no, it's different. A... What? Oh, you can't move. Yeah, A times... Yeah. Whew, my god. Quiz 3. Alright, so it's 9, -3. So let me think. 9, -3. So, okay, it goes down here. And then -3, 1. Like that. This one. Find the inverse of this matrix. Okay, cool. I can do that. So it's going to be 6 minus 4 minus 2 minus 6 divided by its determinant, which is 6 of 18, 24, negative 24 minus 12, so plus 12, so negative 12. So you have 6 divided by 6, negative 1/2, right? And you have positive 1/6. And then you have negative 1/2 again. And then you have 1/3. Okay. Oh my god. Where A is a 3x3 matrix and B is a 3D vector. Find A and B. Oh wait, never mind. It's like the same thing. A is a 3x3 matrix and B is a 3D vector. A times XYZ equals B. So it's 22, 4, 4. You have 6x, 5y, 0z, 0, negative 10, 22, 4, 0, 6. I just saw this question. Yeah, because you can't just move it around. Determinant. So it's going to be 60 minus 60. Yeah. 0, no. Alright. Unit test. Let's see if we can do this. Fuck. Okay, so B is 17. It's 5, 33. 8, 1, 19. 3, 6, 13. 12, 16. Negative 27. Find the values of x and y in this scalar multiplication. Okay. So, negative 5 times x is equal to negative 25. Is it weird to me? Like, look. Wait, let me think about this for a second, because I'm used to scalar multiplication looking like this. Negative 5. Oh, no, doesn't matter. I'm used to it looking like this. But you can have like 100 different numbers here and then same rule applies. So, yeah. So 5x, right? And then negative 4 times negative 5. 180. Right. Look like this. We can rewrite in slope-intercept form. The system has... Does it have a matrix? What is that? 14 times negative 6. Okay, it has a matrix. Look, you can see the slopes are different. So it does. Okay. Choose the interpretation. Okay. 3 machines and they produce 2 toys. Number of toys that each okay. Machine 1 produces 25 toys. from type toy 2 in a day. Find the difference. Okay, easy. 1 minus minus 1. 0 minus 1. Negative 2 minus 3. Minus 1 plus 2. Find the inverse. Okay. Determinant equals 10. Yeah, because it's 10 minus 0. So it's going to be 1, 10, 0, 8. So okay. 1 over 10, 0. 8 over 10, 4/5, and 1. I think it's 6, 7. True. Consider this matrix transformation. What is the image of 4, 1 under this transformation? Oh, so where does 4, 1 go? Okay. Wait, let me try and verify this myself. Let me go back, because this is like an old lesson. Let me remember. So you have 1, 1, 0, 0 times this times 4, 1. Yeah, there we go. So equals 4, 1. Okay, verify. Just trying to like prove why that one was the way it was. Two, 3 minus 3 minus 1 times 4, 1. So you have 8 minus 12 plus 3 minus 1. 11, negative 13. Geometric effect. Okay, I'm using my hands, by the way, in real life to try and remember it. So negative 1, 0, 0, 1, and the other one's negative 1, 0. So it flips across the y-axis. Okay. What the heck is this? Where each combination of shape choices earns a different number of points for the winner. Matrix A represents a scoring system. It shows the number of points Tom gets. Oh, number of matrix Tom gets. Okay. A negative number means Jerry wins those points. Where rows are Tom's chosen shape. Okay. Matrix B represents the scoring system of a new game where the number of points won in each equation is doubled. So just double the numbers. So it's 6, 4, 6, 0. Linear equations represented by the following matrix solve the system. Okay. Okay, once again, I'm gonna switch to fractions, because screw you. This is going to be negative 3/5. What is that? 1.6. 3/5 plus 5, so 8/5. Negative 2/5 and 7/5. XY equals negative 3, negative 2. This shit easy, bruh. Yeah. So 7/5, negative 3/5, 2/5, and negative 8/5. And then divide by the determinant. Determinant equals... Oh my god, bro. Why is it fracted? I don't like that. So negative 3/5 times 7/5. What is that? Negative 21, 25 minus negative 16. So it's automatically a plus. 16 over 25. Okay, so the answer is 21 plus 16. So 5 over 25, so 1/5. So divide by 1/5. That means that you multiply this by 5, right? Because if 7 over 5, if you divide... if you multiply by 5... No, if you divide by 5, it's going to be like this. Like times 1 over 5. But its determinant is 1/5, so you multiply it by 5. Okay. So 35 over 5, so this one is going to be inverse is 7, 2, negative 8, negative 3. Right? You just have to cancel the... Because dividing by a fraction is the same as multiplying. So just cancel the fractions. Okay. That's our inverse. And then now multiply this to this one. So negative 3. So this gets cancelled. And then negative 2. So it's going to be negative 3, negative 21, 24, plus 2, negative 4, 6, minus 25, 30. Please. Am I wrong? No! No! No, it's the final one. Damn, it could have been perfect. Ugh. I don't care. What's the answer? Oh no. Oh no. Fuck, I got the signs wrong. How though? What's the determinant again? Oh my god. Because the determinant's negative. Guys, this happens like even when I was in high school. I always get these questions wrong because of the fucking negative sign, bro. Every time it's always a fucking negative sign, bruh. And my downfall, bruh. Now all these signs are flipped. Negative, negative, positive, positive. This one's gonna be negative. This one's now positive. This one is now negative. This one is now positive, and this one's now negative. So it's gonna be 25 minus. Wait, what? Yeah, look. Ah, ah ha ha ha. Oh my god, bro. You do something to drill negative into your head. You're so right, bro. Look at that. I literally got the number, but it's like the fucking sign, bro. Like, just switch the sign. Oh my god. No! No, why do you rank me down, Khan Academy? What are you doing? That's not nice. Bruh. Come on, man. It's not fair. Kramer's rule, bro.
Systems of equations in the context of transformation.
I don't want to do dot product and cross products. Let me just go to Kramer's rule. Okay. Probability. This should be easy, right?
In a previous video, I've talked about linear systems of equations, and I sort of brushed aside the discussion of actually computing solutions to these systems. And while it's true that the number crunching is typically something we leave to the computers, digging into some of these computational methods is a good litmus test for whether or not you actually understand what's going on, since that's really where the rubber meets the road.
Yeah, look, Kramer's rule right there.
Here, I want to describe the geometry behind a certain method for computing solutions to these systems, known as Kramer's rule. The relevant background here is understanding determinants.
You can just solve the equations normally. True. It's like a fun little
bit of dot products, and of course linear systems of equations. So be sure to watch the relevant videos on those topics.
Oh, I didn't learn dot products.
Unfamiliar?
You know what? Fine. Wait, what is a dot product? I already forgot. Oh. Is this absolute value? What is this? Oh yeah, it's the magnitude. So magnitude of A times the magnitude of B cosine theta, or if you have the x and y values, ax bx plus ay by. All right. I like studying, but I cannot study for like long periods of time, bro. Look at my Charlie Kirk video. I cannot study for like 5 hours. I can't do that. Maybe for like 2 hours every single day, but like not. I can't do it for like 3 hours, bro. I'm actually gonna die. Imagine the two vectors you're taking the dot product of to form a triangle. The dot product is just double the area of that sine triangle.
Traditionally, dot products are something that's introduced really early on in a linear algebra course, typically right at the start, so it might seem strange that I've pushed them back this far in the series. I did this because there's a standard way to introduce the topic, which requires nothing more than a basic understanding of vectors, but a fuller understanding of the role that dot products play in math can only really be found under the light of linear transformations. Before that though, let me just briefly cover the standard way that dot products are introduced, which I'm assuming is at least partially review for a number of viewers. Numerically, if you have two vectors of the same dimension, two lists of numbers with the same lengths, taking their dot product means pairing up all of the coordinates, multiplying those pairs together, and adding the result. So the vector 1, 2 dotted with 3, 4
So it's going to
would be 1 times 3 plus 2 times
8.
4. The vector 6, 2, 8, 3 dotted with 1, 8, 5 3 would be 6 times 1 plus 2 times 8 plus 8 times 5 plus 3 times 3. Luckily, this computation has a really nice geometric interpretation. To think about the dot product between two vectors, v and w, imagine projecting w onto the line that passes through the origin and the tip of v. Multiplying the length of this projection by the length of v, you have the dot product v dot w. Except when this projection of w is pointing in the opposite direction from v, that dot product will actually be negative. You have the dot. Multiplying the length of this projection that passes through the origin and the tip of v. Multiplying the length of this projection by the length of v, you have the dot product v dot w.
Okay.
Except when this projection of w is pointing in the opposite direction from v, that dot product will actually be negative. So when two vectors are generally pointing in the same direction, their dot product is positive. When they're perpendicular, meaning the projection of one onto the other is the zero vector, their dot product is 0. And if they point in generally the opposite direction, their dot product is negative.
Okay.
Now, this interpretation is weirdly asymmetric. It treats the two vectors very differently. So when I first learned this, I was surprised that order doesn't matter. You could instead project v onto w, multiply the length of the projected v by the length of w, and get the same result. I mean, doesn't that feel like a really different process? Here's the intuition for why order doesn't matter. If v and w happened to have the same length, we could leverage some symmetry. Since projecting w onto v, then multiplying the length of that projection by the length of v, is a complete mirror image of projecting v onto w, then multiplying the length of that projection by the length of w.
Well, because
Now,
the
if you
projector,
scale-
the projections, yeah, look at that. They make the same right triangle.
One of them, say v by some constant like 2, so that they don't have equal length, the symmetry is broken. But let's think through how to interpret the dot product between this new vector,
I'm gonna
2
guess that the area of the triangles that they make are the same.
times v, and w. If you think of w as getting projected onto v, then the dot product 2v dot w will be exactly twice the dot product v dot w. This is because when you scale v by 2, it doesn't change the length of the projection of w, but it doubles the length of the vector that you're projecting onto.
Yeah,
But on the other hand, let's say you were thinking about v getting projected onto w. Well, in that case, the length of the projection is the thing that gets scaled when we multiply v by 2, but the length of the vector that you're projecting onto stays constant. So the overall effect is still to just double the dot product. So even though symmetry
the 2v dot w is equal to 2 times v dot w. Wait, let me rewind.
getting pictured that your doesn't v product 2v dot w will be exactly twice the dot product v dot w. This is because when you scale v by 2, it doesn't change the length of the projection of w, but it doubles the length of the vector that you're projecting onto.
Yeah.
But on the other hand, let's say you were thinking about v
Oh, okay.
getting projected onto w. Well, in that case, the length of the projection is the thing that gets scaled when we multiply v by 2, but the length of the vector that you're projecting onto stays constant.
So one of the two stays constant. Alright, bet.
So the overall effect is still to just double the dot product. So even though symmetry is broken in this case,
No,
the
I'm
effect
wrong.
that this scaling has on the value of the dot product is the same under both interpretations. There's also one other big question that confused me when I first learned this stuff. Why on earth does this numerical process of matching coordinates, multiplying pairs, and adding them together have anything to do with projection? Well, to give a satisfactory answer, and also to do full justice to the significance of the dot product, we need to unearth something a little bit deeper going on here, which
Alright.
often goes by the name duality.
Duality.
But before getting into that, I need to spend some time talking about linear transformations from multiple dimensions to one dimension, which is just the number line. These are functions that take in a 2D vector and spit out some number. But linear transformations are, of course, much more restricted than your run-of-the-mill function with a 2D input and a 1D output. As with transformations in higher dimensions, like the ones I talked about in Chapter 3, there are some formal properties that make these functions linear, but I'm going to purposefully ignore those here so as to not distract from our end goal, and instead focus on a
learn how to
certain
use
visual
Manim.
property that's
Make some cool
equivalent to
shit
all
like
the
this.
formal stuff. If you take a line of evenly spaced dots and apply a transformation, a linear transformation will keep those dots evenly spaced once they land in the output space, which is the number line.
Okay.
Otherwise, if there's some line of dots that gets unevenly spaced, then your transformation is not linear. As with the cases we've seen before, one of these linear transformations is completely determined by where it takes I hat and j hat. But this time, each one of those basis vectors just lands on a number. So when we record where they land as the columns of a matrix, each of those columns just has a single number. This is a 1x2 matrix. Let's walk through an example of what it means to apply one of these transformations to a vector. Let's say you have a linear transformation that takes I hat to 1 and j hat to -2. To follow where a vector with coordinates, say 4, 3, ends up, think of breaking up this vector as 4 times I hat plus 3 times j hat.
Okay.
A consequence of linearity is that after the transformation, the vector will be 4 times the place where I hat lands, 1, plus 3 times the place where j hat lands, -2, which in this case implies that it lands on -2.
Oh. That's cool.
When you do this calculation purely numerically, it's matrix vector multiplication. Now, this numerical operation of multiplying a 1x2 matrix by a vector feels just like taking the dot product of two vectors. Doesn't that 1x2 matrix just look like a vector that we tipped on its side?
Yes.
In fact, we could say right now that there's a nice association between 1x2 matrices and 2D vectors, defined by tilting the numerical representation of a vector on its side to get the associated matrix.
This is what I get confused by. It's like, what's the difference? Like, how do I treat these two differently?
Or to tip the matrix back up to get the associated
Confuse
vector.
the hell out of me.
Since we're just looking at numerical expressions right now, going back and forth between vectors and 1x2 matrices might feel like a silly thing to do. But this suggests something that's truly awesome from the geometric view. There's some kind of connection between linear transformations that take vectors to numbers and vectors themselves. Let me show an example that clarifies the significance, and which just so happens to also answer the dot product puzzle from earlier. Unlearn what you have learned, and imagine that you don't already know that the dot product relates to projection.
Okay.
What I'm going to do here is take a copy of the number line and place it diagonally in space somehow, with the number 0 sitting at the origin. Now think of the two-dimensional unit vector, whose tip sits where the number 1 on the number line is. I want to give that guy a name, u hat. This little guy plays an important role in what's about to happen, so just keep him in the back of your mind. If we project 2D vectors straight onto this diagonal number line, in effect, we've just defined a function that takes 2D vectors to numbers. What's more, this function is actually linear,
Wait, what?
since
Let me
it
go
takes
back.
2D vectors straight onto this diagonal number line. In effect, we've just defined a function that takes 2D vectors to numbers. What's more, this function is actually linear, since it passes our visual test that any line of evenly spaced dots remains evenly spaced once it lands on the number line.
Alright.
Just to be clear, even though I've embedded the number line in 2D space like this, the outputs of the function are numbers, not 2D vectors.
Yeah.
You should think of a function that takes in 2 coordinates and outputs a single coordinate. But that vector u hat is a two-dimensional vector, living in the input space. It's just situated in such a way that overlaps with the embedding of the number line.
Okay.
With this projection, we
Black like a phantom. I'm locking in, bro. Because like, man, this shit's making me so
just
Einsteinish.
defined a linear transformation from 2D vectors to numbers. So we're going to be able to find some kind of 1x2 matrix that describes that transformation. To find that 1x2 matrix, let's zoom in on this diagonal number line setup and think about where I hat and j hat each land, since those landing spots are going to be the columns of the matrix. This part's super cool. We can reason through it with a really elegant piece of symmetry. Since I hat and u hat are both unit vectors, projecting I hat onto the line passing through u hat looks totally symmetric to projecting u hat onto the x-axis.
Okay.
So when we ask what number does I hat land on when it gets projected, the answer is going to be the same as whatever U
Oh. It's going to be the same as whatever U hat goes to when it reaches the
hat
x-axis.
lands on when it's projected
Same thing for
onto
J
the
hat.
x-axis. But projecting U hat onto the x-axis just means taking the x-coordinate of U hat. So by symmetry, the number where I hat lands when it's projected onto that diagonal number line is going to be the x-coordinate of U hat. Isn't that cool?
Well, that's cool.
The reasoning is almost identical for the J hat case. Think about it for a moment.
They both pass through that exact place.
For all the same reasons, the y-coordinate of U hat gives us the number where J hat lands when it's projected onto the number line copy.
Bro's learning nothing. No, I swear I'm learning.
And ponder that for a moment. I just think that's really cool. So the entries of the 1x2 matrix describing the projection transformation are going to be the coordinates of U hat. And computing this projection transformation for arbitrary vectors in space, which requires multiplying that matrix by those vectors, is computationally identical to taking a dot product with U hat.
Fuck, man. That's so cool. Let me look at this. So this is the transformation. This is a vector. Is this the U, thing of X?
This is why taking the dot product with the unit vector can be interpreted as projecting a vector onto the span of that unit vector and taking the length. So what about non-unit vectors, units of U hat? And computing this projection transformation for arbitrary vectors. So the entries of the 1x2 the x-coordinate of U hat. Think about it for a moment.
That's cool. Okay. So that's why dot products can technically be considered like projecting, because the same thing can apply if you're U hat. The same thing applies. Yeah, look. We're a vector of ux and of uy. And then you want to know where is x and y. Let's say, for example, let's replace x and y with I hat. So that's going to be 1, 0. It's going to be ux plus uy, but y is 0. So it's just going to be ux. So I hat ends up on wherever ux is 0. That's I hat's projected place, right? That's I hat's projected place on the number line. Same thing for y hat. And if it applies for one vector, it applies for all vectors. That's cool. That's cool. Right. I'm still not really getting it, but I can definitely see why. If you can prove it's correct, if it can work for just the basis vectors, then it can work for all vectors. Why is your channel so brain rotting then live so healing? Man, I gotta take a break every once in a while. Like, making the videos hurts my soul a little bit.
Unit vector can be
So you gotta get it
interpreted
back,
as
Little.
projecting a vector. So what about non-unit vectors? For example, let's say we take that unit vector u hat, but we scale it up by a factor of 3. Numerically, each of its components gets multiplied by 3. So
Okay.
looking at the matrix associated with that vector, it takes I hat and j hat to 3 times the values where they landed before. Since this is all linear, it implies more generally that the new matrix can be interpreted as projecting any vector onto the number line copy and multiplying where it lands by 3.
Yeah, it just change I hat and j, just change ux and uy to like whatever number you want. Let me go back a little bit.
So look of 3 vectors. Numerically, each of its components gets multiplied by 3. So looking at the matrix associated with that vector, it takes I hat and j hat to 3 times the values where they landed before. Since this is all linear, It implies copy and multiplying where it lands
Fuck,
by
I
3.
keep pressing the wrong button.
This is why the dot product with a non-unit vector can be interpreted as first projecting onto that vector, then scaling up the length of that projection by the length of the vector.
Yep.
Take a moment to think about what happened here. We had a linear transformation from 2D space to the number line, which was not defined in terms of numerical vectors or numerical dot products. It was just defined by projecting space onto a diagonal copy of their number line. But because the transformation is linear, it was necessarily described by some 1x2 matrix. And since multiplying a 1x2 matrix by a 2D vector is the same as turning that matrix on its side and taking a dot product, this transformation was, inescapably, related to some 2D vector. The lesson here is that any time you have one of these linear transformations whose output space is the number line, no matter how it was defined, there's going to be some unique vector v corresponding to that transformation, in the sense that applying the transformation is the same thing as taking a dot product with that vector.
All I learned from like there's this association between 1x2 and 2x1.
To me, this is utterly beautiful. It's an example of something in math called duality. Duality shows up in many different ways and forms throughout math, and it's super tricky to actually define. Loosely speaking, it refers to situations where you have a natural but surprising correspondence between two types of mathematical thing.
Whirow, every linear transformation, not even to a line, is a matrix. A vector is the same thing as a matrix. It's just like different dimensions and all that.
For the linear algebra case that you just learned about, you'd say that the dual of a vector is the linear transformation that it encodes. And the dual of a linear transformation from some space to one dimension is a certain vector in that space.
Okay.
So to sum up, on the surface, the dot product is a very useful geometric tool for understanding projections and for testing whether or not vectors tend to point in the same direction. And that's probably the most important thing for you to remember about the dot product. But at a deeper level, dotting two vectors together is a way to translate one of them into the world of transformations. Again, numerically this might feel like a silly point to emphasize. It's just two computations that happen to look similar. But the reason I find this so important is that throughout math, when you're dealing with a vector, once you really get to know its personality, sometimes you realize that it's easier to understand it not as an arrow in space, but as the physical embodiment of a linear transformation. It's as if the vector is really just a conceptual shorthand for a certain transformation, since it's easier for us to think about arrows in space rather than moving all of that space to the number line. In the next video, you'll see another really cool example of this duality in action as I talk about the cross product.
Unlearn what you just learned. Finally, something I can do. Hey, that was the best part of the video. I got to unlearn what I just learned. Whew. One more video and then we can move on. Kramer's rule. Kramer's rule is the last lesson of linear algebra I want to care about. This is like a little much, I'm not gonna lie. So basically, dot products is basically just transformation from 2D to 1D space. That's kind of epic.
Brushed aside the discussion of actually computing solutions to these systems. And while it's true that the number crunching is typically something we leave to the computers, digging into some of these computational methods is a good litmus test for whether or not you actually understand what's going on, since that's really where the rubber meets the road. Here, I want to describe the geometry behind a certain method for computing solutions to these, and be sure to watch the relevant videos on the Kramer's rule is not actually or rusty. But first, I should say up front that this Kramer's rule is not actually the best way for computing solutions to linear systems of equations. Gaussian elimination, for example, will always be faster.
Fuck. Man, I'm gonna end the stream right now, bro. You telling me that this entire thing was useless? Fuck
So
you, man.
why learn it? Well, think of it as a sort of cultural excursion. It's a helpful exercise in deepening your knowledge of the theory behind these systems. Wrapping your mind around this concept is going to help consolidate ideas from linear algebra, like the determinant and linear systems, by seeing how they relate to each other. Also, from a purely artistic standpoint, the ultimate result here is just really pretty to think about, way more so than Gaussian elimination. Alright, so the setup here will be some linear system of equations, say with two unknowns, x and y, and two equations. In principle, everything we're talking about will also work for systems with larger number of unknowns and the same number of equations. But for simplicity, a smaller example is just nicer to hold in our heads. So as I talked about in a previous video, you can think of this setup geometrically as a certain known matrix transforming an unknown vector, xy, where you know what the output is going to be. In this case, -4, -2. Remember, the columns of this matrix are telling you how that matrix acts as a transform, each one telling you where the basis vectors of the input space land. So what we have is a sort of puzzle. Which input vector, xy, is going to land on this output, -4, -2? One way to think about our little puzzle here is that we know the given output vector is some linear combination of the columns of the matrix, x times the vector where I hat lands plus y times the vector where j hat lands, but what we want is to figure out what exactly that linear combination should be. Remember, the type of answer you get here can depend on whether or not the transformation
Literally mathematically impossible to read the past this bullshit. Yeah.
pushes all of space into a lower dimension. That is, if it has a zero determinant. Remember, the type of answer you get here can depend on whether or not the transformation squishes all of space into a lower dimension. That is, if it has a zero determinant. In that case, either none of the inputs land on our given output,
Or all.
or there's a whole bunch of inputs landing on that output. But for this video, we'll limit our view to the case of a non-zero determinant, meaning the outputs of this transformation still span the full n-dimensional space that it started in. Every input lands on one and only one output, and every output has one and only one input. As a first pass, let me show you an idea that's wrong, but in the right direction. The x-coordinate of this mystery input vector is what you get.
Let me go back. So basically, a way to think about it for solving this is like, you have I hat and j hat. If you multiply to some vector, if you have I hat and j hat, no. Remember, multiplication is right to left. So take some random vector. And now you transform it under the rule that I hat goes here and j hat goes here. If this vector follows the rules of this matrix, it goes here. Find the original vector. That's what it means. Yeah, I kind of forgot what exactly
formed
that
version
was.
of it. You hope that coordinate is what you get by dotting it with the second input vector. As a first pass, let me show you vector is what you get by taking its dot product with the first basis vector, 1, 0. Likewise, the y-coordinate is what you get by dotting it with the second basis vector, 0, 1. So maybe you hope that after the transformation, the dot products with the transformed version of the mystery vector with the transformed version of the basis vectors will also be these coordinates, x and y. That'd be fantastic, because we know what the transformed version of each of those vectors are. There's just one problem with it. It's not at all true. For most linear transformations, the dot product before and after the transformation will look very different. For example, you could have two vectors generally pointing in the same direction with a positive dot product, which get pulled apart from each other during the transformation in such a way that they end up having a negative dot product.
Oh, because they're like pointing away from each other.
Likewise, things that start off perpendicular with dot product 0, like the two basis vectors, quite often don't stay perpendicular to each other after the transformation. That is, they don't preserve that 0 dot product. Okay. And looking at the example I just showed, dot products certainly aren't preserved. They tend to get bigger since most vectors are getting stretched out. In fact, worthwhile side note here, transformations which do preserve dot products are special enough to have their own name, orthonormal transformations. These are the ones that leave all of the basis vectors perpendicular to each other and still with unit lengths. You often think of these as the rotation matrices. They correspond to rigid
Rotation
motion
may-
with
okay.
no stretching or squishing or morphing. Solving a linear system with an orthonormal matrix is actually super easy. Because dot products are preserved, taking the dot product between the output vector and all the columns of your matrix will be the same as taking the dot product between the mystery input vector and all of the basis vectors, which is the same as just finding the coordinates of that mystery input. So in that very special case, x would be the dot product of the first column with the output vector, and y would be the dot product of the second column with the output vector. Why am I bringing this up when this idea breaks down for almost all linear systems? Well, it points us in a direction of something to look for. Is there an alternate geometric understanding for the coordinates of our input vector that remains unchanged after the transformation? If your mind has been
Got an email
mulling-
from my university. Hold on. Wow, look at me, bro. So inspirational. What you'll need. I'll check it out. I don't.
over determinants, you might think of the following clever idea. Take the parallelogram, defined by the first
Bro,
basis
I'm
vector,
actually, like,
I hat, and the
locked in
mystery
as hell.
input vector, xy.
Okay.
The area of this parallelogram is the base, 1, times the height perpendicular to that base,
Y.
which is the y coordinate of that input vector.
Okay.
So, the area of that parallelogram is a sort of screwy roundabout way to describe the vector's y coordinate. It's a wacky way to talk about coordinates, but run with me. And actually, to be a little more accurate, you should think of this as the signed area of that parallelogram, in the sense described in the determinant video. That way, a vector with a negative y coordinate would correspond to a negative area
What is
for this
sign?
parallelogram. At least if you think of I hat as in some sense
Bro,
being
the order of how you're
first
learning
out-
everything is so ass. Why? What's wrong?
of these two vectors defining the parallelogram. And symmetrically, if you look at the parallelogram spanned by our mystery input vector and the second basis, j hat, its area is going to be the x-coordinate of that mystery vector. Again, it's a strange way to represent the x-coordinate of that mystery vector.
Because at the end of the course. Oh. Yeah.
Again,
it's whatever.
it's a strange way to represent the x-coordinate, but you'll see what it buys us in a moment.
We'll get to
and
calculus.
just to make
it's
sure it's
fine.
clear how this might generalize, let's look in three dimensions.
I really wanted to do linear algebra because like, I've
Ordinarily,
literally never
the way
learned
you
it
might think
before.
about one of a vector's coordinates,
Oh.
say its z-coordinate, would be to take its dot product with the third of a vector's coordinates,
actually losing
then
my mind. I
present the
actually don't get
x-coordinate, the x-coordinate of that mystery vector. Again, it's a strange way to represent the x-coordinate, but you'll see what it buys us in a moment. And just to make sure it's clear how this might generalize, let's look in three dimensions. Ordinarily, the way you might think about one of a vector's coordinates, say its z-coordinate, would be to take its dot product with the third standard basis vector, often called k hat. But an alternate geometric interpretation would be to consider the parallelepiped that it creates with the other two basis vectors, I hat and j hat. If you think of the square with area 1, spanned by I hat and j hat, as the base of this whole shape, then its volume is the same as its height, which is the third coordinate of our vector.
It would be way easier if you learned in a different direction. Okay. You don't even know what a vector space is? The thing about math is I can just search it up. Let's see what Wikipedia tells me here. If you learn in a different order. I mean, we already learned it. Who cares about like, oh, you could have done it more efficiently. Like, the entire point is that we're learning anyway. Obviously, we're not going to get the most efficient way because we don't know. We don't know. Let's see here. A vector space is a set of whose elements can be added together and multiplied by numbers called scalars. The operation of vector addition and scalar multiply must satisfy certain requirements. Alright, cool. A set of whose elements can be added. Alright. Not bad. It's basically like, isn't like, I cannot even talk, bro! It's like talking about real numbers for like, you know, number theory and countable shit. Or integers, I mean. But this time it's for vectors. It's kind of cool. R squared, R cubed. The fuck? R squared, R cubed. I don't know. That's like really funny to me. You just square R. Set of real numbers with 3 components. Given, okay, where A vector is A1, 2, 3, B, and set of real vectors with, okay, it has an A and B value. Given A is an element of V and scalar C. You get the point.
Vector. And likewise, the wacky way to think about the other coordinates of the vector
can't see what they're doing.
would be
Yeah,
to
I'm
form
on
a
another tab.
parallelepiped using the vector and then all of the basis vectors other than the one corresponding to the direction you're looking for. Then the volume of this gives you the coordinate. Or rather, we should be talking about the signed volume of parallelepipeds in the sense described in the
Parallelepiped, I forgot about that
determinant
word.
video using the right-hand rule. So the order in which you list these 3 vectors matters.
Yeah.
That way, negative coordinates still make sense. Okay, so why think of coordinates as areas and volumes like this? Well, as you apply some sort of matrix transformation, the areas of these parallelograms, well, they don't stay the same, they might get scaled up or down. But, and this is the key idea of determinants, all of the areas get scaled by the same amount, namely the determinant of our transformation matrix.
Yeah, we know that.
For example, if you look at the parallelogram spanned by the vector where your first basis vector lands, which is the first column of the matrix, and the transformed version of xy, what is its area? Well, this is the transformed version of the parallelogram we were looking at earlier, the one whose area was the y-coordinate of the mystery input vector. So its area is just going to be the determinant of the transformation multiplied by that y-coordinate.
Yep.
So that means we can solve for y by taking the area of this new parallelogram in the output space divided by the determinant of the full transformation. And how do you get that area?
Uh-oh.
Well, we know the coordinates for where the mystery input vector lands.
Oh wait, no, it's a
That's the whole
determinant.
point
Never
of a
mind.
linear system of equations. So what you might do is create a new matrix whose first column is the same as coordinates.
Oh, okay. We're now getting to the Kramer's rule
For where the-
Kramer's rule part. So y is equal to, right? So this new area is equal to determinant y, determinant of the original times y, and then just isolate y, and you have this original area. No, I mean the new area. Sorry.
the mystery input.
What is this?
And how do you get that area? Well, we know the coordinates for where the mystery input vector lands. That's the whole point of a linear system of equations.
We
So
know
what you
what?
know where the mystery input vector lands.
Oh,
That's
yeah,
the
okay,
whole
we know
point of a
that.
linear system of equations. So what you might do is create a new matrix whose first column is the same as that of our matrix, but
Mhm.
whose second column is the output vector. And then you take its determinant.
Oh.
So look at that. Just using data from the output of the transformation,
Wow. Wow. That's a cool way. That's very inspirational.
namely the
wow, we
columns
know
of
it
the
already.
matrix and the coordinates of our output vector, we can recover the y-coordinate of the mystery input vector, which is halfway to solving the system. Likewise, the same idea can give us the x-coordinate. Look at the parallelogram we defined earlier, which encodes the x-coordinate of the mystery input vector, spanned by that vector
We're looking
in
for
j
x
hat.
in this case.
The transformed version of this guy is spanned by the output vector and the second column of the matrix, and its area will have been multiplied by the determinant of that matrix. So, to solve for x, you can take this new area divided by the determinant of the full transformation. And similar to what we did before,
Okay.
you can compute the area of that output parallelogram by creating a new matrix whose first column is the output vector and whose second column is the
The area is determinant. I think the one thing I don't understand, I understand that the bottom, right? Determinant of x. I don't understand why this one is also a determinant. Maybe it's just how much it's squished.
same as the original matrix. So again, just using
I'm
data
kind
from
of
the
getting it. Kinda.
output space, the numbers we see in our original linear system, we can solve for what x must be. This formula for finding the solutions to a linear system of equations is known as Cramer's rule. Here, just to sanity check ourselves, plug in some numbers here. The determinant of that top altered matrix is 4 plus 2, which is 6, and the bottom determinant is 2, so the x-coordinate should be 3. And indeed, looking back at the input vector we started with, the x-coordinate is 3. Likewise, Cramer's rule suggests that the y-coordinate should be 4 divided by 2, or 2, and that is in fact the y-coordinate of the input vector that we were starting with. The case with 3 dimensions or more is similar, and I highly recommend that you take a moment to pause and think through.
Okay, cool. So it's basically another way to think about how to solve for the x and y values. At least I can visualize it. All right. Is this gonna be easier than the other ones? Oh, a die or a permanent. 35 plus 15, 50. Okay. Oh my god, bro! Oh wait, I was right. I just put 50 instead of 50%. There we go. Okay. I think I learned this before. Maybe. Chat, I don't know if I want to learn this. Should I? Wait, Unit 9 is series? And limits and continuity? What? Oh, I guess this is, I mean, this is calculus already here. Unit 9 is binomial theorem. Oh. Like for 2 dimensions, then he'll say it's obviously n dimensions. Okay, so we're in probability. So I guess we have to do this one also. I definitely have to learn all this off stream. Like one part of me that doesn't want to skip. I'm not gonna lie, but like there's some stuff it's like I don't really want to though. Let me think. Let me think about my schedule. Because like I have to do math, I have to do physics. I kind of know what the binomial theorem is. It's something to do with like the triangle, right? And then you can just kind of, and then you have to like, you can get the coefficients of x like to the 100th plus y to the 99th or something like that. What was it? This is Khan Academy. I don't know. I'm happy I finished at least my take on linear algebra. I'm happy I finished it, but woo, quite a lot. So Unit 9 is series. Geometric series. I mean, this is literally a formula, bro. Geometric series is literally just a formula. Summation notation, I mean, I know that. Binomials, Pascal's triangle, yeah, this one. Arithmetic. Why is arithmetic series like right like 2 steps ahead of... Okay. I do know there are some things I want to do, I want to learn, and other things I don't want to learn. But let me think, because like I remember I skipped complex numbers because like who cares? I don't give a shit, honestly. Okay, here's the plan, all right? We will do... Unit 8's not really a thing for... I don't really care about probability and shit. This is like statistics and shit. That's not what I'm doing. I will do like maybe until here, and then unit 9 I'm gonna go geometric series. I already know it's just a formula that I don't want to do. I did not learn binomial theorem, so I guess I'll do this. So I'm gonna skip these two because like bruh. Maybe I'll do summation notation intro. You know what? Let's see. So from j equals 0, 1, 2, 5. Oh, never mind. This is like easy. 2 minus 0. So 2 plus 1, 3. Never mind. 2 plus... K to 2. 1, 4 plus 6. Right? If it's 2. Never mind. Never mind, bro. I don't have to learn it. Oh my god, what? I was like, what? What? Oh shit. It's a sigma.
To the first times 3. This is by 1. We're
Oh. See, like, if it's like geometric series and shit, like, if it's like summation and permutations and combinations and shit like that, bro. Like, bruh.
Three to the...
I mean, you use one formula. All the lessons that are like one formula, I'm not even gonna bother, bro. Okay, I'm gonna do Venn diagrams. I'll do multiplication rule. I'll do probability until quiz 2, and then series I'll just do binomial theorem. That's it. Arithmetic I already know. Just another formula you have to remember. And then limits. Okay, so tomorrow's stream we're gonna do these two and possibly limits, maybe, possibly 100, maybe, I don't know. Squeeze theorem. Oh, it gets squeezed in between two functions. Yeah. Yada 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 yada. Let's see, how many hours? We're at 2 hours 18. Alright. Well, GG to linear algebra. GG, I'm gonna finish the stream. So tomorrow I'm gonna finish these 2 units and then do a little bit of a calc or calculator. Alright. I'll end the stream for now. We're getting there. Thank God, bro. We're out of linear algebra. Like, yes, I can go further, but it's not needed. I just wanted to learn just enough so at least, like, you know, I kind of have the basics done. But yeah, pretty good. I actually might learn the non-calc off stream so that tomorrow's stream can just jump straight onto limits, which I already know Calc 1. I know limits, I know derivatives. But once again, no, we gotta start from the bottom, you know, so we can review. I don't miss some random shit. What course is Twin gonna do? You'll find out. Alright, thank you everyone for watching. Pretty good progress today. And yeah. I wanna eat lunch!